Good day. The purpose of this video is to derive the moment summation equation for Newton's laws for rigid bodies. This is Chapter 17, Kinetics of Rigid Bodies. Previously, we looked at in Chapter 13 a system of particles, which is what a rigid body basically is. And that system of particles could be acted upon by forces, which create moments about various points. It could be acted on by applied moments. Anyway, we said that the sum of the force vectors is equal to mass times acceleration vector of the center of gravity, and we can split that up into x and y force equations. But now we need to derive the rotational version of Newton's law. And as I say on page 7 of your lecture notes handout, that gets a little tangly depending on the point about which we take moments. Now, the most general case is what happens if we take moments about some arbitrary point P, which maybe isn't even fixed, maybe it isn't even the center of gravity. We'll do a general moment summation, and then we'll talk about how things get simpler if that point also happens to be the center of gravity, or if that point happens to be fixed. So in this figure, I've got a rigid body, and here's an arbitrary point P, which can be moving, and I've put an xy origin at point P. Now these x and y directions are fixed, and P is at the origin. We're going to define all our position vectors in Cartesian form with I and j coordinates. Let's take one lucky particle I with mass mi. Let's assume that our body has angular velocity and acceleration, and I'll make them both counterclockwise, although they need not be. So this little particle I, has an acceleration vector, and it's acted on by capital F external forces and lowercase f internal forces from other nearby particles. Now, let me see. If we want to take the sum of the moments about point P, well, if we take the sum of the moments about P due to forces on particle I, we can express a moment as a position vector r, as shown in the figure, crossed with a force. So r cross capital Fi is the moment about P due to external forces. R cross lowercase fi is due to internal forces. For the individual particle, we know that the sum of the forces, external and internal, is equal to the mass of the particle times the acceleration vector ai of the particle, which means that the moments about P we could express it as r cross f, or we could express it as r crossed mi ai. Alright, so the sum of the moments is r cross mi ai. Now we can write vector ai in terms of vector ap, because I and P are 2 points on the same rigid body, and we'll express the vector ai in terms of AP because P is the point that we're interested in right now. Just like any other 2 points, we can write ai is equal to AP plus ai relative to P, which is going to be AP plus ai relative to P normal plus ai relative to P tangential. So if I go back to this figure, I can draw a vector. That's not very good. I can draw a vector from I towards P. Let's see. And that's going to be ai with respect to P normal. And if alpha is in the direction that I've shown, I can draw another vector which is ai with respect to P tangential, perpendicular to a line from P to I. Now, I know in solving problems I've encouraged people to use a scalar approach to finding relative motion. But for the purposes of this derivation, I'm going to use cross products to express the relative acceleration of I and P. I with respect to P normal. In our section in Chapter 13 about fixed axis rotation, we said the normal acceleration could be expressed as omega squared r in the negative r direction. And the tangential acceleration could be expressed as the alpha vector crossed with the position vector. So now, the moments about p due to forces on the particle I are going to be, as I said before, r cross mi ai, which is going to be mi r cross, because mi is a constant, so I can do mi r crossed with the acceleration. And that acceleration, ap minus omega squared r plus alpha cross r. Now if I expand this out one cross product at a time, I'll have mi r cross, let me see, I'll have mi outside of r cross ap plus, if I do mi r crossed with minus omega squared r, that's going to be mi outside of minus omega squared r cross r. Now r cross r, if you cross a vector with itself, it's going to give you 0. Okay, so the second term here goes away. Mi r crossed with alpha cross r, now that doesn't go away. That becomes mi outside of r cross alpha cross r. Alright, so do we have anything useful yet? Well, almost. Okay, so for AP, let's see. Look at this beauty. That is a Montegrappa Il Teatro La Fenice di Venezia sterling silver fountain pen commemorating the 200th anniversary of that magnificent Venetian theater. A handmade luxury fountain pen fashioned in blue celluloid, precious silver, inspired by the chandeliers, the pillars, and the exquisite Rococo filigrees that decorate every interior surface of La Fenice, whatever in heaven's name that means. Our previous result was that the moments about p due to particle I is mi outside of r cross ap plus r cross alpha cross r. Now, r vector is a vector from point P to particle I, and its coordinates are x, y, with respect to the origin. So if I draw a particle up here, okay, I'll draw a vector r that's going to go from the origin to particle I, and its coordinates are simply x and y. Now the r bar vector, that's the vector from P to the center of gravity of the body. Okay, so arbitrary particle I was not at the center of gravity. Here's the center of gravity located at coordinates x bar and y bar from the origin. It has acceleration vector ag. I'm going to make a substitution into this relation. Instead of r, I'm going to write xi plus yj. So that's the vector I've just drawn over here. I'm going to recognize that moments about p, that moment vector is going to be in the k direction because we're looking at two-dimensional motion. Also, alpha and omega are going to be k vectors. So when I make these substitutions, the vector mp about I becomes mp about I in the k direction, which becomes mi outside of, I had r cross ap up here. Now I've got xi plus yj crossed with ap. AP I can express as apxi plus apyj. I'm just breaking that into I and j components. Now I've got r cross alpha cross r. So that's going to be xi plus yj crossed with alpha, which is alpha k, crossed with r again, xi plus yj. Alright, so that is another way of writing moments about p due to particle I. Now, if I carry out these cross products, term by term, recognizing that j cross k is I cross k is minus j, and so on, here's the result I end up with. Moments about p due to particle I forces in the k direction equals particle mass mi. I end up with minus y apx plus x apy. I end up with an alpha x squared. Actually, I end up with an alpha outside of x squared plus y squared. And all that's in the k direction. Now, x squared plus y squared, that's the distance r from point P to point I. So I can write what I just wrote as minus y apx plus x apy plus alpha r squared in the k direction. These are moments about point P due to forces on one little particle. The body's made up of a lot of these particles. So to find the total moment summation about P, I've got to add up or integrate the effect of all these moments due to forces on the individual particles. So I'll say, instead of MP about I, I'll say the sum of all the moments about point P. And I'll make my positive direction the same as it is for alpha and omega. I need to, if I sum up or integrate all of the mi minus y apx's, I'm going to have minus the integral or summation over the entire mass of y dm multiplied by apx. I'm going to have the integral over the mass of x dm times apy, and that's for the second term. And for the third term, if I integrate r squared over the entire mass, I get something which by now hopefully looks familiar. I get the integral over m of r squared dm times alpha. That integral of r squared dm, where r is the distance from the particle to point P, that's the moment of inertia about P. So I come down here, and the final thing I'll write here, sum of the moments about point P equals minus, now what's the integral of y dm? The location of the center of gravity with respect to P. If I put an origin at P, y bar is the height of the center of gravity. And from the definition of center of gravity, y bar is integral of y dm over m. Therefore, the integral of y dm must be my bar. So this first term turns into minus y bar m times apx. The second term similarly turns into x bar m apy. And the third term turns into moment of inertia about p times angular acceleration. So that is the sum of the moments about an arbitrary point P, and it's not simply IP alpha. It's IP alpha plus some other stuff. If I go to page 9, suppose P was the center of gravity. That would mean my origin was at the center of gravity. If my origin's at the center of gravity, then x bar and y bar become 0, because I don't have to go anywhere to get from the origin to the center of gravity. So if P happens to be G, the center of gravity, the first two terms go away, and I'm left with sum of the moments about G is IG alpha. If my point P is fixed, then it has no acceleration. APX and APY become 0, and I'm left with sum of the moments about my fixed point equals moment of inertia about my fixed point times alpha. And if I call my fixed point O, as is often done, then I end up with sum of the moments about fixed point O is equal to IO alpha. If you have a fixed point, you can use this equation safely. No matter what's going on with the motion of your body, whether it's fixed axis rotation, translation, general plane motion. You can always use this equation 17.7 from your text. Sum of the moments about the center of gravity equals moment of inertia about the center of gravity times alpha. Okay, so that's all you'll ever need to do. You may find in some solutions and in Hibbler's book, they make the problems a little bit simpler by taking moment summation about point P, and even if P is not fixed or is not the center of gravity, they do moment summations about point P anyway. You'll never have to do that. If you look at some solutions and you're curious, then you can look at the next video in this series, okay? But right now, you know all you need to know to do these rigid body kinetics problems.